So what force provides the centripetal force in this case? Anytime you have a force acting through a rope, what is that force called? This force is the tension force. So in this particular situation, tension provides the centripetal force. It keeps the ball moving in a circle. Now let me give you another situation. Let's say if you have a car, which I'm just going to draw a box, but this is a car, and it's turning on a road. It's following the curvature of a road and it's turning. The fact that it's turning, there's some force that it's causing it to turn. Let's say if it's moving at constant speed and turn at the same time. So there is a centripetal force acting on this car because it's moving in a circular path. What centripetal force, or rather what other force provides the centripetal force in this case? If you see a situation like this, static friction provides the centripetal force. So if you're dealing with a physics problem that has a car turning on a road like this, make sure you set static friction equal to a centripetal force. Now the formula for static friction is mu s times the normal force. It's less than or equal to this quantity. And for the centripetal force, it's mv squared over r. The normal force on a flat surface is simply mg. So in this case, we could cancel m in the expression. So for a word problem that involves a car turning on a road, you have this expression. The coefficient of static friction times the gravitational acceleration is equal to v squared over r. And I'm going to post some links in which you can practice these problems in another video. Now let's say this is the sun, and here we have the earth, and the earth is orbiting the sun. So the earth is moving in a nearly circular path around the sun, which means that there's a force that's acting as a centripetal force in this case to keep the earth moving with uniform circular motion. What force provides the centripetal force in this case? The force that keeps the earth in orbit around the sun is the gravitational force. And so gravity provides the centripetal force in this example. Without gravity, the earth will fly off in a tangent away from the sun deep into outer space. But because we have these two forces that are perpendicular to each other, the earth instead turns in a circular path. And so make sure you understand this. Anytime you have a force that's perpendicular to the velocity component, the velocity vector, the force doesn't speed up or slow down the object. It has no effect on the speed. If it's perpendicular to the velocity of the object, the force can only change its direction. Now let's focus on the equation that relates to the centripetal force acting on the object. It's mv squared over r. So here's a question for you. If the mass of the object increases, what will happen to the centripetal force? Will it increase or decrease? Because the mass is in the numerator of the fraction, increase in the mass will increase the centripetal force. The same is true for the velocity. If you increase the speed of the object, the centripetal force that's needed to keep the object moving in a circle must be increased as well. Otherwise, the object is going to fly out of the circle. So the greater the speed, the more centripetal force that is needed to keep the object moving in a circle. Now, what about if we increase the radius of the circle? What's going to happen to the centripetal force that is needed to keep the object moving in a circle? If you use a wider circle, the centripetal force that's needed to keep it in that circle will decrease because r is in the denominator of the fraction. And so let's focus on questions like these. What effect will the following changes have on the centripetal force acting on an object? So what's going to happen if we double the mass? We know the centripetal force will increase, but by what factor? Now the way in which you can get the answer is as follows. Everything that doesn't change, replace it with a 1. Now, because the mass increased by the factor of 2, replace m with 2. V and r, we're going to replace it with 1. So we get a value of 2. This tells us that the centripetal force will double if we double the mass. Now let's move on to part B. So what effect will it have on the centripetal force if the speed is increased by a factor of 2? So the mass and the radius doesn't change, so we're going to replace it with a 1. But the speed is doubled, so we're going to replace it with a 2. 2 squared is 4, and so this tells us that the centripetal force will increase by a factor of 4. Now what about part C? The radius is decreased by 4. Let's say decreased by a factor of 4. So what should we do? M and V doesn't change, so we're going to replace that with a 1. If the radius is decreased by a factor of 4, that means that it's 1/4 of its original value. So we have 1 divided by 1/4, which is 4. If you want to show your work with that, what you need to do is multiply the top and the bottom by 4. 4 times 1/4 is 1, and so you get 4. Now what about the last one? Part D. What effect will tripling the mass, quadrupling the speed, and plug in half is total force? And that's basically it for this video. So I want to give you a simple introduction into centripetal force.
At first glance, centripetal force looks strange. Consider this situation. The moon revolves around the Earth. The moon has a velocity as shown at a particular instant. However, to make this circular motion, the force should be perpendicular to the velocity, as shown. In mechanics, we generally see velocity in the direction of the applied force. Why, then, is centripetal force perpendicular to the velocity? What is centrifugal force? Let's figure it out with an interesting thought experiment. Consider this tennis ball and assume it's moving on a straight line initially. If you apply force perpendicular to its motion for a short time, the object will deflect, as shown. Its direction changes. Now let's apply the force again, perpendicular to the new direction. The object deflects again. Let's repeat this process. Now, observe the shape the object traveled. It's very close to a circle. If the time interval of applied force is significantly smaller, you will get a more perfect circle. Which means if an object is always acted upon with a force perpendicular to its velocity, the object will move in a circle. This force is known as centripetal force. One more logical conclusion would be that more the centripetal force, more will the object's deflection, or lesser will be the radius of the circle. This means for any circular motion to occur, inward perpendicular force must act upon the object. To get the value of the centripetal force, we should approach the problem analytically and start with the way Sir Isaac Newton defined force. However, there's no fun in an analytical derivation, so we'll animate this method. The conceptual understanding we already developed will really help you in science and engineering. Once again, it is clear from this equation that the lesser the radius of the circle, the more centripetal force will be needed. When the Moon revolves around the Earth, the gravitational force acting between the Moon and the Earth provides the necessary centripetal force. Similarly, when you rotate an object attached to a string, the tension in the string provides the required centripetal force. Consider this spinning wooden block. The frictional force between the block and floor lends the necessary centripetal force. In short, centripetal force should be supplied by some external source such as gravitation, tension, friction, etc. Now that we've learned the concept of centripetal force, the big question is, what is centrifugal force? Consider these examples. When fluid spins in a beaker, as the speed of the beaker increases, the fluid flows outward. Similarly, in this centrifugal casting process, the molten metal always moves to the outer wall. As you increase the speed of this suspended ball, the ball also travels outward. Is there any force called a centrifugal force which is acting radially outward on a rotating object to move it outward? Scientifically speaking, there is no such force as a centrifugal force. It's a pseudo-force. A rotating object always needs a force which is radially inward. Centrifugal force is needed in physics only when you analyze the problem rotating along with the object. In this example, since the observer is sitting inside a rotating cabin, the observer has to add a centrifugal force to analyze the problem. It's a pseudo-force added to convert a non-inertial frame of reference to an inertial frame of reference. If the observer is on the ground, there is no need to use such a force. Now, let's analyze the previous examples using the concept of centripetal force we have developed. As you rotate the ball faster, it moves away. The ball needs a centripetal force. The tension of the rope, more specifically the horizontal component of its tension, provides that force. The tension on the ball has one more responsibility. The vertical component of the tension has to balance the weight of the ball. Logically, as the ball rotates faster, the rope's tension should increase to supply the sufficient centripetal force. However, the weight of the ball does not increase, which means that in order to keep the vertical component of the tension the same, the angle has to increase, like this. This is the reason why the ball moves away as you rotate it faster. The case of the rotating fluid is slightly different. Here again, each fluid particle requires a particular amount of centripetal force to maintain the circular motion. The pressure difference caused by the water level's height disparity generates that centripetal force. The fluid particles at the outer radius obviously need more centripetal force. To satisfy this increasing centripetal force requirement, the fluid surface has to form a curved shape rather than a straight line. When the water volume rotates faster, each particle demands more centripetal force or more pressure difference across the particle. Therefore, the water surface curves more than in the previous case, or you feel like the water is going outward. It's better to avoid using centrifugal force in your scientific or engineering analyses because it's a pseudo-force used only in some special cases. Always work using centripetal force. That's the real force that a rotating object requires.